Good morning, everyone. Thanks for joining the SNAPP seminar today. We have Professor Peter Glynn with us today. And Peter needs no introduction. He's Thomas Ford Professor in Management Science and Engineering Department at Stanford with a courtesy appointment in Electrical Engineering Department. In his long and illustrious career, he has held many positions, and he also served as a chair of MS&E between 2011 and 2015. And he also won several awards. He's a fellow of Informs and fellow of IMS. He was an IMS medallion lecturer in 1995, Informs Markov lecturer in 2014. He was co-winner of Outstanding Publication Awards from Inform Simulation Society 3 times in 93, 2008, and 2016. And he was co-winner of Inform's APS Best Paper Award in 2009. He won the John von Neumann Theory Prize in 2010. And he's going to give the Inform's Philip McCord Morse Lecture in 2020. In 2012, he was elected to the National Academy of Engineering. And one of the prominent service activities he did for our community is that he founded the Stochastic Systems Journal, and he served as editor-in-chief for several years. And in addition, he also served as editor-in-chief for Journal of Applied Probability and Advances in Applied Probability from 2016 to 2018. Today, he's going to talk about 3 applications of Poisson's equation. So Peter, on to you.
Thank you very much, Siva, for that very gracious introduction. It's a real pleasure to have an opportunity to speak to this community, and thank you very much to the organizers for organizing this seminar series and inviting me to participate. So today I'm going to talk about Poisson's equation, and I'm going to give 3 recent applications of Poisson's equation I've been involved with. Probably some of you will be aware of the central role that Poisson's equation plays. Maybe some of you are not aware of this important role that Poisson's equation plays. So at least some portion of this will be tutorial, at least the first part of the talk. And then I'm going to talk about 3 different applications of this very important set of ideas. So the outline of the talk, as I've just indicated, is I'll briefly review Poisson's equation. Poisson's equation arises naturally in pretty much any setting in which you're interested in studying equilibrium behavior of a Markov chain or Markov process. Then I'm going to talk about 3 relatively recent applications of Poisson's equation with which I've been involved. First is Poisson's equation for boundary functionals of queuing-like systems, systems that exhibit reflection at the boundaries of a state space. Then I'm going to talk about Poisson's equation for computing equilibrium sensitivities. And finally, I'll talk about a more recent application with which I've been involved with Ramesh Johari and Mohammad Rasouli, involving the use of Poisson equation type ideas in the analysis of adaptive experimental designs, in particular in the context of temporal interference. So the work on boundary functionals is joint with Rob Wang, and the work on equilibrium sensitivities is joint with Chang-Han Rhee. So what is Poisson's equation? Poisson's equation is most easily described in the context of a finite state Markov chain having state space capital S. We have a transition matrix P of xy. P of xy represents the probability of going from x to y in one transition. And there are 2 different versions of Poisson's equation that are in some sense dual to one another. One is the function version of Poisson's equation, in which the right-hand side of Poisson's equation is a function, which I'm indicating here as f. So the equation involves a coefficient system I minus p hitting the function g, g being the unknown solution to Poisson's equation. That product has to be equal to the right-hand side f. So we're given an f, we want to compute a g from this linear system. Now, I minus p, as we all know, p being a stochastic matrix, 1 is an eigenvalue of a stochastic matrix, so I minus p is singular. So we're going to come back and talk about that in a moment. Then there's the dual version of this involving distributions or measures. In that case, the unknown is the distribution or measure nu, hitting I minus p from the left-hand side. So as usual in the world of Markov chains and Markov processes, we're going to view the functions as being encoded as column vectors and view distributions or measures as being encoded by row vectors. Okay, so I said a moment ago that I minus P is a singular matrix. That means, of course, that it can't be that this set of linear equations is solvable for all possible right-hand sides F or for all possible right-hand sides eta. So that means there must be some restrictions on the class of right-hand sides for which we can compute a solution. So we can see quite easily just by hitting both sides of the function version of Poisson's equation by the stationary distribution pi, which of course exists uniquely in the context of a irreducible Markov chain that is finite state, that of course pi times I minus P is equal to 0, which means the left-hand side of this equation is 0, which means, of course, that pi times F has to be equal to 0 if this equation is going to be solvable. And then for the measure valued version of this, the distribution valued version of this, if we hit the linear system on the right-hand side by the column eigenvector associated with the eigenvalue 1, namely the vector E, which is 1 in every entry, which is just a constant function. We see again that the fact that the row sums of a stochastic matrix are always equal to 1, that E hitting on the right-hand side, I minus P, has to be equal to 0, which means that, again, the left-hand side is 0, which means that we have the solvability constraint that eta E is equal to 0. In other words, the distribution eta is a signed distribution in which the sum of the eta of x's is equal to 0. So that's the solvability constraint for distributions or measures. And of course, when you see a linear system that looks like this, it's natural to try to solve this by applying I minus P inverse to both sides. And we know that when the spectral radius of a matrix is less than 1, that I minus P inverse can be described as an infinite geometric sum of powers of that matrix. So you might try to do the same thing in this context, try to somehow express I minus P inverse, which we know doesn't quite exist because we know there's a singular matrix I minus P, and we might try to express this as an infinite geometric sum. We see that that goes to pieces because, of course, the infinite sum of powers of a transition matrix P obviously computes out to infinity in this finite state setting. So that isn't a sensible approach, but maybe something close to that works. And what's close to that is to recognize that, of course, if we now add on the assumption that not only is P irreducible and finite state space, but also aperiodic, then we know that the n-step transition probabilities corresponding to the nth power of P converges to the equilibrium probabilities. The equilibrium probabilities, of course, don't depend on the initial state. So when you write this in matrix form, P to the n converges to a rank 1 matrix in which every row is identical, in particular given by the stationary distribution vector little pi. And of course, that rank 1 matrix can be written as a product of the column vector E with the row vector pi. Pi again being the stationary distribution vector for the Markov chain. So now we see if we hit both sides of this relationship by the column vector F. Remember, we're assuming that pi F is equal to 0 for solvability. We see that what we get is P to the n again is converging to E times pi. Pi times F on the other hand is equal to 0. So we see that P to the n F is converging to 0 as n goes to infinity. And that convergence, of course, in the finite state aperiodic setting is geometrically fast. So P to the nf goes to 0 quickly. And similarly, if we look at the measure valued version of this, eta times P to the n, again, P to the n converges to E times pi. That's the rank 1 matrix capital pi. Eta times E is equal to 0. That's the solvability constraint that we imposed on eta earlier. which means that, again, eta e times pi is equal to 0, which means eta p to the n is convergent to 0 geometrically fast. So in this finite state space setting, we know that p to the n f goes to 0 geometrically fast, eta p to the n goes to 0 geometrically fast. So it is the case that this infinite sum converges and is a meaningful infinite sum, which suggests that maybe we can solve this Poisson's equation by just postulating that the infinite sum of powers of p to the n hitting the function f is a solution of the vector function version of Poisson's equation, while the infinite sum of eta p to the n, summed from n equals 0 to infinity, is a solution of Poisson's equation for the distribution version of Poisson's equation. So indeed, that approach works. There's a completely satisfactory way of solving Poisson's equation in this finite state setting. And in fact, it will, as we will see in a few moments, it generalizes quite nicely beyond the finite state setting as well. Now, again, because of the fact that I minus P is a singular matrix, these solutions are not going to be unique. In particular, if we go back to the function version of Poisson's equation, and we see that G is a solution of this equation, it's pretty clear that if you just add on any constant function to G, that will again be a solution of Poisson's equation, because of the fact that constant functions are annihilated by I minus P in this stochastic context. And similarly, when we find a solution U to the measure version of Poisson's equation, if we add on any constant times the equilibrium distribution, that will also be a solution of Poisson's equation. So Poisson's equation does not have unique solutions, but you'll see in the applications that we have in mind that that non-uniqueness doesn't create any difficulty for us. Now, the argument that I just gave, in which I asserted that p to the n times f converges to 0 geometrically fast, obviously draws upon the fact that the Markov chain is a aperiodic Markov chain. But with a simple modification of this argument, we can see that the aperiodicity is actually unnecessary, and we can actually solve Poisson's equation in generality when the Markov chain is finite state and irreducible. Now, the conclusions that we've just drawn here in the context of finite state Markov chains also generalize to the infinite state setting in at least two different ways. So first of all, in the context of discrete state space, when we have a Markov chain that has, again, is irreducible, irreducibility, of course, is just implying that we have a unique stationary distribution, and we assume that the Markov chain is positive recurrent, then if the function f that we're trying to solve Poisson's equation for is such that it is integrable or summable with respect to the equilibrium distribution, so this is just the constraint that the reward function is such that it is integrable with respect to the stationary distribution. And of course, again, as always, that it's centered, that pi f is equal to 0. Then again, the same conclusions that we reached earlier hold, namely, there always exists a solution to Poisson's equation, and the uniqueness, at least within the class of integrable solutions of Poisson's equation, is unique up to an additive constant function. Now there's a similar kind of result for the measure valued version or the distribution version of Poisson's equation. All right, so now that also generalizes to context of continuous state space Markov chains. In particular, the most tractable class of continuous state Markov chains is the class of Harris recurrent Markov chains, in particular positive Harris recurrent Markov chains. And again, in that context, if the right-hand side of the function version of Poisson's equation is such that it is integrable and that it is centered so that pi f is equal to 0, then again, there exists a solution of Poisson's equation for pi almost every x. Because for almost every x in the state space, you can find equality in Poisson's equation. And again, Poisson's equation is a usable technology in that context because of the existence of solutions to the corresponding linear system. Now, why is it that Poisson's equation plays such an important role in the world of Markov chains and Markov processes? Well, at least in the function version of Poisson's equation, the key issue is its connection to Martingale's. So let me now make that connection clear. So again, let's imagine that we have a finite state, S-valued Markov chain. The state of the Markov chain at time n is given by xn. Now we're going to think about a simple additive functional of the Markov chain. So imagine that we're summing up rewards over time. F of x is the reward earned in state x. So f of xj then is the random reward earned by the Markov chain at time j. And now Sn is going to be summing up all of the rewards from time 0 to time n minus 1. So there are n sum n's in Sn. Now, if we want to represent such an additive functional or such a cumulative reward or cumulative cost as a martingale, well, martingales have constant expectation over time, which suggests that if we want Sn to be close to a martingale, we're going to need to demand that the function f is already centered at its equilibrium expectation, so that pi f is equal to 0. So let's imagine now that we've centered this function f to have pi f equal to 0. Now, what is it that's really cool about Poisson's equation? It's that if we now substitute in the fact that G solves Poisson's equation, then, of course, I minus P times G is equal to F. And if we just substitute that in for f of xj, here's what we get. And so each term in this sum is a g of xj minus a pg of xj. And that can essentially be written as, well, the sum of the g of xj's in this term is summing from j equals 0 to n minus 1. So that's pretty much exactly what I have here, except this is summing from j equals 1 to n. So I need to add on a x0 term and subtract off an xn term to keep my equality with j equals 0 to n minus 1. And then with regard to the second term in this quantity, the pg of xj minus 1s are summing from 0 to n minus 1, just as they are in the sum for Sn. So this term is exactly in equality with what we have over here. And so as a consequence, I get this, this additive representation of Sn. And the thing that's important about this representation is that g of xj minus pg of xj minus 1 turns out to be a so-called Martingale difference. And what do I mean by that? I mean that if I take that jth Martingale difference, here it is down here, and I condition on the history of the Markov chain up to time j minus 1. Of course, conditioning on the history up to time j minus 1 is the same as conditioning on just the state of the Markov chain at time j minus 1 because of the Markov property. And then we see that the one-step conditional expectation of g of xj given the xj minus 1 is just, of course, a sum over the g values of the probability of going from the state occupied at time j minus 1 into the new state y. So this is exactly in correspondence with this conditional expectation over here. And of course, this sum is nothing more than pg of xj minus 1. That sum is nothing more than just take the matrix P, hit it with the column vector G, that's a new column vector PG, and evaluate that in the xj minus first entry. So the fact that so this this sum is just equal to this, and we get a 0 out of this at the end. So it has exactly the conditional expectation property that a Martingale difference needs to have. Now, what is it that's nice about Martingale differences? Two different things. First of all, we know that the conditional expectation of a Martingale difference is 0. That means obviously its unconditional expectation is 0. The other thing that's important about Martingale differences is that they act very much like independent mean zero random variables. And that means that, for example, the variance of a sum of Martingale differences is just the sum of the variances. So pretty much the same calculus that we know for sums of independent mean zero random variables holds for sums of Martingale differences. And it's maybe not going to be a surprise in view of that, the cleanest way of developing central limit theorems for additive functionals of Markov chains is to apply the Martingale structure that we've just identified. So in particular, if we sum up the f of xj's and divide by root n, well, let's go back to this representation that we have here. That's basically, here's the sum of the f of xj's. We want to divide that by root n. That's the same as taking Sn and dividing it by root n. That's the same as taking this sum of Martingale differences, dividing by root n. And we have a g of x0 and g of xn sitting over here that we're also dividing by root n. These terms are obviously typically going to be converging to 0 as n tends to infinity. So they have no impact on the limit distribution. And the Martingale central limit theorem applies to this sum of Martingale differences divided by root n. As I was saying earlier, Martingale differences behave very much like sums of mean zero independent random variables. That's the prototypical setting for validity of a central limit theorem. And so it's no surprise that a Martingale central limit theorem derives immediately from that Poisson equation representation. So this is an important observation in a number of different settings. So first of all, in the context of performance analysis, when you want to look at variability behavior of sums of rewards or sums of costs, this Martingale central limit theorem describes the first order variability of such a cumulative reward or cumulative cost. It arises obviously quite naturally in the world of statistical inference when you're looking at estimation problems that involve Markov-dependent random variables. The Martingale central limit theorem, and in particular Poisson's equation, arises quite naturally in that setting, especially and in particular when you're using method of moments type ideas. And of course, another important aspect of the Martingale structure that we've just identified is again that all of these Martingale differences have mean zero, which means that when you compute the expected value of Sn, you get a lot of simplification. So in particular, if H is now a cost function, reward function, remember, we're always applying Poisson's equation to centered H's. So we can write this H function as a sum of the equilibrium expectations plus its centered version. Here's the contribution from the equilibrium expectation. Here's the contribution from the solution of Poisson's equation corresponding to the function h. And we see that we get a large n approximation for the behavior of the expected value of a cumulative reward or a cumulative cost. Now, this same kind of structure and behavior appears in the context of optimal policies for average cost MDPs. If you look at the Hamilton-Jacobi-Bellman equation that describes the optimal policy in that context, you'll see that at least under the optimal policy, that what is sitting implicitly inside that HJB equation is exactly Poisson's equation. In fact, you'll recall, if you're aware of that literature, that HJB equation involves an unknown constant. The unknown constant is just the equilibrium expectation that arises out of this Poisson's equation in the context of centering. Okay, so now I want to turn to Poisson's equation in continuous time. So one way of writing the Martingale representation that I just described is that G is a solution of Poisson's equation if pi f is equal to 0, and if this sequence of random variables is a px martingale, in other words, a martingale for every initial state x adapted to the filtration of the Markov chain. And that suggests that a very natural continuous time analog to this is to assert that G is a solution of Poisson's equation if pi f is equal to 0, and if G of x of t plus the integrated reward up to time t is a martingale. For technical reasons, in general, we won't be able to assert that it's a full martingale. We'll only be able to assert that it's a local martingale. But typically, through example-dependent argumentation, we can often extend the local martingale property to a full martingale property. So this is the appropriate definition at some level of what it means to solve Poisson's equation in the context of a continuous time Markov process. So let me now illustrate this in the context of Brownian motion. So we want to find a function g such that g of b of t plus the integral 0 to t of f of b of s ds is a martingale. And now all that we need to do is to apply Ito's formula to this. So we compute the differential of g of b of t, and we see that we get the gradient of g of b of t hitting the Brownian motion b of t. And then we get an additional term from the Ito calculus involving the Laplacian PDE operator delta. So this is the Laplacian down here, hitting the function g evaluated at the time b of t. And then, of course, when we computed the differential of this, we get f of b of t times dt. And what we'd like is that g has been chosen so that we get a martingale back. Now, this stochastic integral term, in great generality, is going to be a martingale. In particular, it's always going to be a local martingale, which means that we will get a local martingale from this if we choose g such that this term here is equal to minus f of b of t. In other words, if we choose g so that Laplacian of g divided by 2 is equal to minus f, then we get our desired martingale. The reason that I wanted to go through this specific example is this actually, I believe, is the origin for why this class of equations is called Poisson's equation. This is the classical Poisson's equation for partial differential equations that goes back to the 1800s. So when you specialize Poisson's equation to Brownian motion, then you get the classic Poisson PDE from classical applied mathematics. So Poisson's equation in the Markov chain Markov process context is a generalization of that PDE. Okay, so I believe that we traditionally stop here for a minute or two for questions. So let me stop here.
Looks like we don't have any questions.
Okay, good. All right, so I'm going to continue then with the first example that I wanted to illustrate of more recent applications of Poisson's equation, so you can get some sense of other settings in which Poisson's equation arises, and some setting of some sense of the flexibility of this particular mathematical approach to the study of additive functionals. So let me now talk about two-sided reflected Brownian motion. So this is a Brownian motion process that is evolving on an interval 0b. And we have a Brownian motion process, let's say, starts off at some point in between 0 and b, evolves, hits the 0 boundary, hits the b boundary. That's a two-sided reflected Brownian motion. When it's on the interior of the state space, it's just evolving like a Brownian motion with drift mu and volatility sigma. Now, in order to keep the process between 0 and b, you have to have some pushing processes at the zero boundary, that is the process L of t. That's going to be an increasing process that pushes the process back into the positive interval 0b. And correspondingly, there's going to need to be another pushing process at the b boundary that is pushing to the left. That's why we have a minus sign here. So u of t is another increasing process with the minus sign in front of it. It's a decreasing process. It's pushing the process back into the interval 0b. Now, the amount of pushing that the process needs to do at the right boundary at b effectively corresponds to the diffusion analog to the loss process for the underlying associated queuing model. So two-sided reflected Brownian motions come about as heavy traffic limits, diffusion approximations to queues with loss at the upper boundary. And this pushing process, u of t, in particular, corresponds to the amount of loss in the diffusion limit that's occurring at the upper boundary. So again, if we apply Ito's formula in this context, we can see that, again, we want to choose the function g in such a way that only the stochastic integral survives, because stochastic integrals are known to be local martingales. So you just choose g to make all of these other pieces go away. So in order to do that, we need to put LG g prime of 0, g prime of x of t dl of t equal to 0. Now L only pushes at the origin, so dl of t is only positive when x of t is equal to 0. So we can make this equal to 0 if we choose g prime of 0 equal to 0. Similarly, we can make this equal to 0 if we set the derivative of g at b equal to 0. And then since we're trying to make this process a martingale, we need to choose LG equal to minus f. By choosing LG equal to minus f, when we bring this term over to the left-hand side, we're going to get dg of x of t plus f of x of t dt. That's exactly what we need here in order to get the martingale representation. So that's a quick exposition of what Poisson's equation looks like for this reflected process in the context of a two-sided reflected Brownian motion. Here's the differential equation on the interior, and here are the two boundary conditions that go with reflection at the origin and reflection at B. Now, from the standpoint of the queuing interpretation, it's pretty clear that one of the most interesting things to compute in this context is to somehow get central limit theorems, laws of large numbers, and other such results for the loss process itself. So loss process itself is u of t. So now let's turn to the question of what about if we wanted to get a central limit theorem for u of t rather than some integrated reward function that is integrated over interior states of the reflected Brownian motion process. So now we're looking at trying to find a g such that g of x of t plus u of t minus ct can be represented as a martingale. And now once again, we can play exactly the same game that we did in the previous slide. We just apply Ito's formula in this context. What we're aiming for is that we find a function g such that the differential of g of x of t plus du of t minus c dt is equal to the stochastic integral. Again, a stochastic integral we know is going to be a local martingale. And so what is it that we need to do to achieve that? Well, you want to put LG equal to C on the interval 0b. You want to put G's derivative at 0 equal to 0, and we want to put G primed of B equal to 1. By putting G primed of B equal to 1, remember, U of T only increases at the boundary B, so du of T is only positive when X of T is equal to 0. This should, by the way, be G primed of X of T sitting here, as also with the dl of T term. And that means that we can make this term equal to 0 if make this term equal to minus du of t if we put g prime of b equal to 1. Then we bring this term over to the right-hand side. We'll have a plus du of t sitting on the left-hand side. This term will go away because of this boundary condition. This term here will be C times dt, which again, when we bring it over to the right-hand side is going to, or left-hand side is going to be a minus C dt. And now we're going to have this thing equaling this stochastic integral, hence the Martingale representation that we were seeking. So that is a illustration of how Poisson's equation generalizes from simple additive functionals that are integrals over the state space into more complicated boundary functionals like the pushing process U of t at the right boundary, the so-called loss process in that Q. Now there's a similar thing that you can do if you have more complicated processes than Brownian motion. If you have, for example, a two-sided Lévy process. A Lévy process is basically a Brownian motion plus a Poisson process that induces additional jumps given by the random variable zi coming in. So x of t minus x of 0 is equal to mu t. We have the standard Brownian motion term that we saw in the previous example. We have the pushing process at the origin, the pushing process at B. And then in this example, since this process also has jumps, so in particular, there will be times at which this process tries to jump out of the interval 0b, because the Lévy process also has these additional jumps occurring at the Poisson times of the independent Poisson process. Here, n of t, by the way, is the Poisson process. This process will try to jump to the right of B from time to time. It'll try to jump to the left of 0 from time to time. And in the context of a queuing model, what would happen when you have loss is that the process, when it tries to jump, a big jump, of course, would correspond to a large number of customers arriving to the system instantaneously. That instantaneous excess above the level B would just be pushed back to the right boundary B. Similarly, there'd be a pushback to 0. And these pushbacks to B and pushbacks to 0 associated with the jumps are just given by these two terms. Once again, it could be that you would like to have a law of large numbers or a central limit theorem for the amount of pushing or the amount of loss that's occurring at the upper boundary B. And again, you can go through pretty much exactly the same approach that we did in the previous RBM case to determine the appropriate integral PDE that needs to be solved. And here's what it is. I'm not going to go through the details. It's just pretty much the same story as what we did in the two-sided case when we were looking at trying to get a central limit theorem or a Martingale representation for U of t. And here's what comes up. You have to solve the integral PDE, LG equal to K on the interior of the state space. And once again, you have the two associated boundary conditions that G prime to 0 is equal to 0 and G prime to B is equal to 1. And the right-hand side in this case is equal to the constant C being the equilibrium rate at which loss is occurring per unit time. So C is an undetermined constant in solving this equation. When you solve this equation, you solve not just for G, but also for the constant C. Here's something that is basically the instantaneous amount of loss occurring per unit time that's induced by the Poisson process. And here is the integral differential operator L. You can see it has the sort of standard diffusion piece here, if you're familiar with that literature. And then it has some jump components. This is the jump component associated with jumping above level B, or trying to jump above level B. And here is the rate at which the process is trying to jump below level 0. So this is, again, an approach to extending Poisson's equation to boundary functionals now of Markov processes that also involve jumps in addition to diffusion. So all this extends easily to general additive functionals. You can go to the multidimensional context. Now you get PDEs, potentially with integral PDE operators. You can deal with reflection. You can deal with pretty much any other type of boundary condition that you want to add on. And I might add that for this last example, you can do a lot of explicit computation. So in particular, in the one-dimensional case, when you have a Levy process with two-sided reflection, you can do very explicit calculation of the characteristics of these additive functionals of these loss processes in that setting. Okay, that was the first of these applications of Poisson's equation I wanted to talk about. Now let me talk about the second application. So this involves the measure valued version of Poisson's equation. Now we're talking about, we're going to apply this in the context of a statistical problem. So let's imagine now that theta is some unknown statistical parameter that drives the dynamics of the Markov chain. That means, of course, that P of theta, the transition matrix, or in a continuous state space context, the transition kernel, depends on the unknown statistical parameter. And of course, if we're interested in understanding the impact of uncertainty in an unknown statistical parameter to equilibrium expectations, we're going to be interested in understanding the sensitivity of the equilibrium distribution pi of theta to uncertainty in the estimate of theta. So the natural vehicle for doing this is to apply a statistical method known as the delta method that basically assumes smoothness of the expectation of interest, in this case an equilibrium expectation, on the statistical parameter theta. That means basically computing a derivative of the equilibrium distribution with respect to the unknown parameter theta. So we're now talking again about sensitivity analysis. So if you want to formally understand what system of equations you need to solve, you just start off with the equilibrium equations depending on theta. Just formally differentiate both sides. We get the second line on this slide. Bring the unknown pi prime of theta over to the left-hand side. We get the third line. And notice that on the matrix P of theta is stochastic for all theta. So of course, that means that its row sums are equal to 1 for all theta, which means P of theta E is equal to E for all theta. That means that when we differentiate it with respect to theta, we get P prime to theta times E equal to 0, which means that this distribution over here, pi of theta times P prime to theta, if I write mu equal to pi of theta times P prime to theta, well, mu E is equal to 0 since P prime to theta E is 0. That's the solvability condition that we need for Poisson's equation. So as a consequence, this equation should typically be solvable for the unknown u. So that means that it should be that we can compute pi prime to theta as a through the measure valued version of Poisson's equation. That means in particular that if I have an estimate theta hat for the true unknown theta, and I want to look at pi of theta hat minus pi of theta f, so I want to look at the sort of plug-in value of the equilibrium expectation versus the true value of the equilibrium expectation under the true value of theta. That will involve the derivative of the equilibrium distribution hitting the function f. That's just mu hitting the function f. And then we get theta hat minus theta. That's coming out of a first order Taylor expansion in that derivative. And again, in great generality, for example, when you have maximum likelihood estimators, when you have method of moments estimators, these quantities will typically satisfy central limit theorems. So that's sitting over here. And so as a consequence, this uncertainty in the equilibrium expectation will indeed be normally distributed for large values of n here being the unknown statistic, being the statistical sample size. And we have all of that being pre-multiplied by the equilibrium sensitivity nu multiplied by f. So that's where Poisson's equation arises in this sensitivity setting. Now, if you want to look at things in the infinite or continuous state space setting, we can view P of theta, for example, as an operator on a particular function space. This is a very natural one that arises all over the world of Markov chains and Markov processes. Just this, it's a weighted soup norm space. It's a set of all functions h, such that the supremum over x of the absolute value of h of x divided by some weight function w of x is finite. And there's a corresponding dual space on the space of distributions or measures. And now the easiest way to sort of generalize formally what I did on this slide, this was just a formal calculation, but if you want to make everything rigorous, you can easily do that in the setting of even infinite or continuous state space Markov chains, assuming that you're willing to make the right assumptions about the problem data. And the natural assumption to make is to somehow try to show that this equation will always have a solution. And in order to do that, we'd like this I minus P of theta to have an inverse on the solution space of Poisson's equation, the set of mu's that have this property. And you can do that by assuming that I minus P of theta plus the rank 1 operator capital pi of theta has an inverse on these spaces LW and MW, and that the transition matrix or transition kernel P of theta is differentiable in the suitable norm on this space. And the proof is very straightforward, relatively easy to do. The only problem with this approach, the proof in infinite state space and continuous state space looks almost identical to the rigorous proof that you would give for a finite state space Markov chain once you appropriately generalize to these function spaces LW and MW. The only problem is that in the infinite states continuous state space context, this assumption that this operator has an inverse is a heavy mathematical assumption, because it basically implies that the Markov chain or Markov process X is geometrically ergodic. Now that covers many examples, but there are some examples that it doesn't cover. So for example, if you look at one of our prototypical queuing models, the MG1Q, and the Polizek-Hinshin formula tells us that the expected number in system and the expected time in system should be differentiable in a rate parameter and service time distribution, basically under finite variance type assumptions on the service times. Polizek-Hinshin formula says the mean service time, mean time in system depends on service time through the second moment. That suggests that so long as the service time has a second moment, that the mean number in system in equilibrium, mean time in system in equilibrium should be differentiable in that rate parameter. And unfortunately, when the service times don't have exponential moments, where they're heavy-tailed, so to speak, those Markov chains are not geometrically ergodic. So this example suggests that the operator-based approach that I just described here for establishing differentiability of equilibrium expectations and so forth is going to fail to cover queuing models like this, in which the service times are heavy-tailed random variables having finite variance but not exponential moments. So if you want to cover examples like this, you have to do something a little bit different. And the thing that you can do to cover examples like this is to not use an operator theoretic approach that is too heavy-handed to cover these types of examples. Rather, what you can do is take the formula that we had for pi prime to theta. Here it is. Multiply both sides of this by the function f. Let's imagine that we're trying to establish differentiability for that particular performance measure f, and then recognize that this quantity over here is just a solution of Poisson's equation. And then the way that you try to argue differentiability of this particular performance measure is not by using operator theoretic methods, but by making assumptions on existence of Poisson's solution to Poisson's equation for this particular right-hand side f. And then you can do that through Lyapunov-based arguments, and you can get much, much weaker assumptions on the differentiability of these equilibrium expectations by following that kind of approach. So when you do this, you basically get minimal conditions for differentiability of equilibrium expectations. So the trick here is to work directly with the function g corresponding to a given right-hand side. Don't use the operator theoretic approach that is more straightforward and easy to use, and then you'll get good conditions for those types of examples. The last example that I wanted to talk about is the adaptive experimental design example that arises, for example, in the context of temporal interference. As an example of temporal interference, let's imagine that we have a ride-sharing platform. There are a couple of different experimental designs that they want to test against one another. Let's say design 1 and design 2. The dynamics of the system under each one of those designs can be modeled, let's say, as a Markov chain. And what we're interested in is identifying which of these two Markov chain dynamics is going to give us the best long-term reward. And in order to evaluate that, we're basically trying to compare the equilibrium reward under design 1 to the equilibrium reward under design 2. And one potential way of estimating this difference in equilibrium reward is by potentially switching back and forth using first chain 1 dynamics, then chain 2 dynamics, and judiciously switching back and forth from one dynamic to another, hopefully estimating these two quantities more and more accurately over time. So the question is, what sort of switching design should we adopt? And let me now just describe that in a bit more detail. So at any time n, we're going to be running this ride-sharing platform. We can choose either to use type 1 dynamics or type 2 dynamics for the next transition. So in particular, based on the history observed up to time n, we'll use either type 1 dynamics or type 2 dynamics, and we can randomize between the choice, Pn being the probability that we choose type 1 dynamics, 1 minus Pn being the probability that we choose type 2 dynamics, and of course these Pns should be adapted to the history up to time n. It should be non-clairvoyant. So what's the best policy in this setting? So I'm going to just describe how you might analyze this. And we'll see that Poisson's equation arises in a very natural way in this context, both the measure valued version and the function valued version. So first of all, when we apply this type of policy, how should we estimate the transition probabilities? Well, the natural estimate is the so-called non-parametric maximum likelihood estimator for the transition probabilities for each of the two chains. So you just look at the fraction of time that you were in a given state X and that you applied, let's say, to choose the next dynamics from chain I. So this is the total number of times that we were in state X and chose to sample from chain I. And then you just see the fraction of those times that we actually went to state Y in the next transition. So it's the natural estimator. Just look at the total number of experiments and look at the fraction of time that we went to state Y on the next transition. So once you have the estimated transition matrix, so this is the XY entry of the estimated transition matrix, we can now look at the equilibrium distribution that goes with that. So that's the non-parametric maximum likelihood estimator for the equilibrium distribution. Not surprisingly, given the discussion that I just went through on sensitivity analysis, we'll view pi hat n of I as being a perturbation from pi of I. So it turns out that there's a very natural analog to the derivative representation that we had for pi primed of theta that emanates in this particular setting as well. So if you look at the difference of the estimated equilibrium distribution from the true equilibrium distribution, that looks like the true equilibrium distribution multiplied by the perturbation in the transition matrices multiplied by that inverse operator that I discussed a few slides back. So an inverse operator is what in the world of finite state Markov chains would be called the fundamental matrix or fundamental operator. And now, as I was saying, so here's basically the measure valued version of Poisson's equation implicitly arising. And now what we're actually interested in is understanding the behavior of the estimate for a particular reward function that I'm now encoding as the function f. And so now I'll hit both sides of this first equation, multiply by f on both sides. And then I have here the fundamental matrix or inverse operator to Poisson's equation hitting the function f. That's going to be my solution, my function valued solution to Poisson's equation for the reward function f, or more particularly for its centered reward function. And so now you see on this slide, Poisson's equation arising in two fundamental ways. First of all, the measure valued version of Poisson's equation, and secondly, the function valued version of Poisson's equation. So both of them are arising in this analysis. And now, next thing to do is to recognize that when you look at the estimated transition matrix minus the true transition matrix hitting the Poisson's equation, so solution of Poisson's equation G of I, that turns out that it can be written, maybe not surprisingly, given the fact that we've got Poisson's equation sitting there. That can also be written as a sum of Martingale differences, in which the Martingale differences depend on both the state I, the state X, the particular chain I that I'm actually using to run the dynamics at time J. And these Martingale differences are not just orthogonal in J as standard Martingale differences are, but they're also orthogonal in both I and in X. So these dj of I of X's are orthogonal random variables in J, orthogonal random variables in I, orthogonal random variables in X. So as much uncorrelatedness as you would possibly hope for in this context, which is going to make computing the variance of the estimator particularly simple. And when you apply the Martingale central limit theorem in this context, it's not going to be a particular surprise, I don't think, that the Martingale central limit theorem is going to be easily applied, and that the variance is going to be easily reducible to something that can be explicitly computed. So again, we're looking at this equation. This is basically what we're trying to get a estimate of. And you get a central limit theorem involving the second moments of the Martingale differences. It involves the equilibrium probabilities, and of course it involves the long run fraction of time that we sample chain I while in state X. And then the natural thing to do, optimal policy should be one that minimizes variance. So now you choose the gamma I of X's in an optimal way, which means that we have to minimize this over gamma I of X's. And that turns out to be a nonlinear convex optimization problem. So this is a strictly convex optimization problem. It's not an objective function which is linear in these gamma I of X's as would occur in the MDP setting, which means that when you solve for the optimal set of gamma I of X's over the feasible region will be a policy polyhedron that looks identical to the types of policy polyhedra that arise in the MDP setting. The optimal point, the minimizing variance point, is not going to be on the boundary of that convex region, but will be on the interior of the convex region, which means that the optimal policy will typically be randomized. So you get quite a different looking sort of optimal policy in this setting than in the standard setting. So this is the third application of this whole idea. So let me conclude then. Poisson's equation is one of the fundamental tools of applied probability. I hope I've argued effectively that it arises in many equilibrium and steady state settings. And then finally, continuous time to Martingale connection is an indispensable way of thinking about Poisson's equation. Without that Martingale connection, it's very difficult to derive general Poisson type representations for general additive functionals in the continuous time setting, particularly in the SDE jump diffusion context. So that concludes what I wanted to say. So thank you very much.
Let's thank Peter. I'll start with a question. So about the second part that you talked about, the second application on sensitivity analysis,
Yeah.
that's very closely related to policy gradient theorem, which is very popular in reinforcement learning, right? Can you comment about that connection?
Yeah, I mean, I think it indeed is very closely connected. I mean, I talked about it primarily in the context of statistics, just to motivate it in this talk. But of course, it could also have been that I was trying to optimize some sort of function over a class of policies indexed by theta. And then, of course, this gradient would play a critical role in that context. So these Poisson equation representations for the sensitivities also naturally translate into Monte Carlo algorithms that can be applied for computing these sensitivities. So indeed, there's a close connection to that world as well.
Okay, got it. Thanks. If anyone has a question, feel free to go ahead and ask.
So Shiva, can I ask a question?
Yeah. Sure, go ahead.
Okay. So thanks, Peter, for this wonderful talk. This is Abhishek from OSU. I was wondering if the Poisson equation, so you mentioned that there are two places where Poisson equations can be applied when Markov chain is irreducible, and the other one was when it is Harris recurrent. Does it also apply to Feller chains?
Yes, it would. Yeah, absolutely.
Okay.
So the main thing is that you have to have a Markov chain for which you know for the given performance measure of interest that you have convergence in this infinite sum. So again, I'm implicitly assuming that the F has been centered.
Right.
As long as you can establish that P to the n F goes to 0 sufficiently quickly that this sum converges, Poisson's equation is immediately applicable. So it doesn't necessarily require the types of regeneration structures that occur in Harris recurrent Markov chains. If you have a Feller chain for which you have a contractive structure available that guarantees that P to the n F goes to 0 quickly, Poisson's equation would also be a totally viable technology in that context as well.
Understood. Yeah, that'll be very helpful. Okay, thank you very much.
Yep, sure, great question.
If there are no other questions, I'll ask one more question. So on slide 20, this was when you were talking about, this was when you were saying even if you don't have geometric ergodicity, you can use Poisson's equation if you mentioned about using a Lyapunov argument to argue that the Poisson equation has a solution. Can you say more about that?
Right. So geometric ergodicity would basically be a setting in which you have some function W that has this type of behavior off compact sets. So the type of Lyapunov condition that comes up in this setting is a weaker condition in which you're seeking some function h, for which this is true. So
Oh, I
pH
see.
is less than or
Okay.
equal to h minus g. So we're not requiring now that the h be a multiple of g,
Okay.
as we
Got it.
would in the geometrically ergodic setting. So there's a much weaker Lyapunov style condition than the geometric ergodicity condition.
Okay.
Yeah.
Can I ask a question?
Absolutely.
Hi, Peter. How are you?
Hi, good.
I missed 80% of your talk, but I got the idea. Have you discussed Poisson equation in connection to optimal stopping at all?
I didn't do it in this talk, no.
Oh, okay.
Yeah.
Okay. All right. Thanks. That's all.
There are many other applications. I mean, Poisson's equation arises all over the place, and you know, at least in the form that I described it here, I focused entirely on equilibrium type calculations. So that is a very particular structure and a very particular set of technical issues that arise in that context.
Okay, since there are no more questions, let's thank Peter again before we end the talk.
Thank you.